me pause. I'll probably still just be wearing the mask, so it doesn't bother me that much. It shouldn't bother you that much. Everybody close your Chromebooks. We're about to get started. I've had to wear like respirators for work for like 8-hour shifts. So it's, you got to wear a mask. You got to breathe through something. It's all about health. When I welded, and we'll talk about my jobs later in the year, but when I welded for several years, is anybody in welding class? You weld for like an 8-hour shift and you go home and your boogers are literally black. And you just know that you're breathing in like soot and smoke, and you do that for years, it's not going to be good for your health. Like you're probably going to die of lung cancer or have something bad. So real quickly, I didn't steal because it was workplace equipment, but I got one of the paint respirators that the painters wear to keep paint from going in their lungs. And I wore one of those all day. I even had to cut like the sides of my mask away so my welding mask would go down over the paint respirator. But it was terrible. Like it was super hot. My mouth sweat all day. It was less comfortable to breathe. But I'd rather do that for 8-10 hours a day than only live to like the age of 60 instead of living to 80 or 90. So, and not that that's the comparable thing with these masks, but just wear the mask. When you get home, you take them off. It's not a big deal. You get in your car, you take them off. I don't know if any of y'all are driving now, but it's not a big deal. Just wear the mask, keep it up above your nose, and everybody will be good. I feel bad for y'all because y'all got to eat lunch in the same room. I get to eat lunch in my own private little hole over here in the classroom. I know the other teachers are judging me for not eating lunch in the teachers' lounge, but I don't care. I'm not going in there until all this is over. I'll just sit here and watch YouTube videos while I eat my lunch by myself. So today we're starting on something new. Today we're going to start to talk about radioactivity, which is the one part of the class that we're really not concerned with electrons. So most of the time your nucleus doesn't do anything. An atom of carbon or gold or silver or whatever is more than likely going to stay an atom of that element. Let's say it's silver. It's probably going to stay an atom of silver forever. It doesn't matter what you do with it. You can mix it into medicines. You can put it into some sort of metal jewelry. You can do all sorts of stuff with it. It's probably going to be silver till the very end of time unless something crazy happens. But there are some elements that do change. They do switch from one element to another. They go down this chain of progression. And those are basically called radioactive elements. And so we're going to go through that today. We're going to learn a little bit about it, what they are, what they do, how they do it. And then we'll start on some problems to kind of discuss how we identify those and how we talk about them. So the whole thing about radioactive elements is they're unstable. If they were stable, they wouldn't be radioactive. They stay the same thing forever and never change. But if they're unstable, they're going to have to change. They're going to have to get to a point of stability. And that's why they become radioactive, to try to seek out that stability. So the stability of an atom is determined by its ratio of neutrons to protons. And I kind of mentioned this before. All the protons are what charge? Positive. Can you stick two positive magnets together? No, they're going to push each other apart. And so actually what you need to put all these protons that are positive in the same small little nucleus is you need neutrons. Neutrons are like the packing paper or the styrofoam peanuts. They let you kind of separate everything just enough to fit it all in the nice little box that you have and make it this nice, neat little package that is an atom. So for every proton, you need a certain number of neutrons. And the neutrons kind of allow you to fit everything in there. They talk about strong nuclear force for a second. This is one of the, I'm not going to say it because I don't know. It's either 4 or 5 fundamental forces of physics. I have a physics minor, and so I'm really ashamed that I don't remember this right now. I'm going to say that it's 4 fundamental forces of physics, but strong nuclear force is one, along with weak nuclear force, gravity, and I don't remember the other one, to be honest. I don't think it's magnetism. It's something else. I'll have to look it up in a second. But anyways, strong nuclear force is a strong force, hence the name, that only acts over very short distances, like within the nucleus of an atom. To hold protons and neutrons together, it's almost like a gravity for the nucleus. If enough neutrons are present, the strong nuclear force can overcome that electrostatic repulsion of the protons trying to push each other apart. And so the protons always want to push each other apart. If you get enough strong nuclear force, they're not going to do that. They're all going to stay together. Heads up in the back. Let's pay attention. So you need this balance between the strong nuclear force and your positive protons pushing each other apart, which is that electrostatic repulsion. Now, how do you get this balance? You're looking for this stability. It's all about how many protons you have to how many neutrons you have. And for the most part, at the very beginning of the periodic table, it's a 1-to-1 ratio. So the first 20 atoms, which, thank you for getting your periodic table today. For those of y'all that got it. The rest of y'all should know by now. Need your periodic tables. Yeah. I know it's him. So look, what's your 20th element? One of y'all that has it, what's the 20th element?
Calcium.
Calcium is the 20th element. So all the way from hydrogen, all the way up to calcium, those are usually going to be pretty stable atoms. There's nothing really radioactive all the way up from, what's it called? Yeah, from hydrogen up to calcium. Not very radioactive. Notice what's right before calcium? Is potassium radioactive? That's why bananas are radioactive. They have potassium in them, and potassium is some potassium. It's just slightly radioactive. Maybe one day we'll actually look at that, and I'll explain that a little bit better. But yeah, radioactive energy. We do. It doesn't hurt us. It's not good. Bananas are actually good for you. It's not bad for you that bananas are radioactive. It's part of the baseline radiation that we all have. But in these first 20 atoms, your ratio is 1-to-1. They say the ratio is 1.0. That basically means for every one neutron I have, I also have one proton. 1-to-1 ratio from protons to neutrons. In larger atoms, the more protons you have, the more neutrons you're going to need to pack all those protons in and separate them. So above 20, you start to need more and more neutrons. So notice with calcium, the number of protons you have is 20. If you look at the bottom number, which is protons plus neutrons, your atomic mass, it's what? 40. So yeah, 40.07, just over 40. So that means you have 20 protons, 20 neutrons. Go up to something like gold. Gold has, well, let's do mercury because it's even. Mercury has 80 protons. What is 80 plus 80? 160. But mercury doesn't have 80 protons. Its total weight is 200. So instead of 80, it actually has 120 neutrons. So for mercury to be stable, it needs almost 50% more neutrons to make sure that it actually stays stable. So the more protons you get, the more neutrons you need. And they have a chart that shows you this in just a second. As the number of protons increases, the number of neutrons must increase. What we call this when we chart this out is called the belt of stability. If you're in the belt of stability, you're stable, you're not going to be radioactive, everything's going to be great. If you're not in the belt of stability, something's going to have to change to kind of move you back towards that. So here's the chart. Here is the wonderful belt of stability. Notice, here's calcium, 20 protons, 20 neutrons for a total mass of 40. Everything below this is just about 1-to-1. For every proton you have an extra neutron. Now, as you get further up with more and more protons, notice this is your 1-to-1 line where protons equals neutrons. You have more and more neutrons that you need up here to actually be stable. Now, if you fall within this white little strip here, hey, heads up in the back. Let's wake up. Keep your head up off your arm. Yeah. So if you fall in this white little strip here, you're going to be neutral. You're going to stay the same atom probably forever. If you fall outside of this, either in the blue range or in the gray range, you either have too many neutrons or too many protons, and something's got to go. And when they get rid of those, it's going to slowly move you back towards this belt of stability. And once you get there, you're going to be nice and stable, and everything's going to stay the same. So let's look at some examples of what can happen. When you have radiation, anything that's radioactive, the radioactive part of what it's doing is called radioactive decay. Decay is what we call this because you have something actually leaving your molecule. In the same way, this is going to be a little bit morbid, but what are things that decay? Dead things. So whether it's like an animal or a body or like a plant decaying, it literally has molecules and elements and minerals that leave that thing, and it slowly just like decomposes down into almost nothing. That's what decay is doing. That's what your elements are going to do. They're going to have little parts of them leave and go somewhere else, so they get back to where they want to be. So it's the emission of radiation from unstable nuclei. It occurs because your radioactive isotope is unstable. It either has too many neutrons or too many protons. If it had the right amount, it wouldn't be radioactive. It would be stable. Radioactive isotopes decay until they turn into stable isotopes. That's always the end goal. So it's not just going to like disappear. It's going to turn into a different element. And usually once it gets to a stable element, it's no longer radioactive. A lot of your bigger radioactive elements, not all of them, but many of them, they radioactively decay until they get to the element lead. And then once they get to lead, they're usually stable and they'll stay lead for a long time. And so given enough time, your radioactive stuff usually turns into lead. Sometimes it's something completely different, but that's one of the more common ones, which is kind of ironic because what are the vests made out of that we use to protect ourselves from radioactive elements? Lead. And so we use like the former husk of a radioactive element to protect us from it. An isotope plotted above the belt of stability has too many neutrons. It's going to try to get rid of neutrons. And if it's underneath, it has too many protons. What did that say? All elements with more than 83 protons are radioactive. So there you go. On the periodic table, find 83. That's bismuth in the light blue there. Anything above that, so this bottom row of the periodic table and the bottom row of the lanthanides and actinides, all of those are going to be radioactive. There's no question about it. You can have radioactive stuff above that, but everything past 83 is unstable and it's going to be radioactive. Some things last for hundreds of millions of years. There are some radioactive elements that literally only last for like a fraction of a second. They radioactively decay very, very quickly. Several types of radiation can be emitted during radioactive decay, and we're going to learn about those now. So they talk about nuclear radiation. You have three things, actually four, because there's two types of beta particles. We'll see that in a second. You have alpha particles, beta particles, and gamma ray, or gamma radiation, also known as gamma rays. So an alpha particle is essentially just a with two protons and two neutrons. So mass number is 4, 2 protons plus 2 neutrons. Your nuclear charge is +2 because I have 2 protons. What element has 2 protons? Helium. Helium has 2 protons. This is literally just a atom of helium that gets shot out of your nucleus to go on and do other things, do its helium thing. And so sometimes they use the A for the alpha. Most of the time, they're going to use the actual He like it's a helium atom. It has 2 protons, 2 neutrons. It doesn't have any electrons. So this has a +2 charge. It's a positive thing. Alpha particles is actually what Rutherford shot at the gold foil. When he did his gold foil experiment, he was shooting alpha particles at it to see what happened. When alpha radiation occurs, an alpha particle is released from the unstable nucleus. And what does it do? It removes 2 protons and 2 neutrons. So this is actually the math that you're going to do. They're going to give you an equation, and you're going to have to balance it or figure out what new element you created or what radiation you have. So for example, if I have polonium, which is radioactive, it has 84 protons. Anything above 83 is definitely radioactive. If I have 84 protons and I shoot out 2 protons in my helium atom, how many do I have left? 82. So I find the 82nd element, which happens to be, lead. Pb is lead. So like I mentioned, a lot of these turn into lead. And then you do the other math, 211 total protons and neutrons. I shoot out 4. What's 211 minus 4? 207. And so a simple subtraction or addition on your math here. Treat the arrow like an equal sign, but you can't go back and forth. You can't put lead and helium together to make radioactive polonium. It only goes one direction. So this is the kind of math that you're going to do in the problems. Not too bad. So remember, alpha particle has 2 protons. It's essentially a helium atom. 2 protons, 2 neutrons. Beta particles are a little different. Beta particles are where we get weird. It's a type of nuclear radiation composed of an electron emitted from the nucleus it has a nuclear charge of -1. Now, here's the thing. Everybody needs to think about this. Are there electrons in the nucleus? No. And this is where things get weird. Remember, I mentioned this before. I didn't make a big deal out of it. But I wanted to make a distinction that neutrons don't have no charge at all. They have what charge? A neutral charge. And neutral is different from no charge. We treat it as no charge, but actually what's happening here, I do have a marker over here. I'm going to draw this and then I'll erase it later. A neutron isn't just empty. It actually technically has both charges. It has a positive and a minus. And so do the plus and the minus cancel out? And so overall, does your neutron have a charge? No. But when we talk about beta radiation, now you kind of see what's happening. I'm going to have an electron shoot out of the nucleus, and it's going to turn one of my neutrons into a proton. So if I take this negative charge and I literally shoot it out in radioactive decay, what's left over in that neutron? A positive charge, yeah. And so my neutron gets switched to a proton in this radioactive decay. And this is actually important because in beta particles, you have 2 protons and 2 neutrons leave. That didn't really change my ratio very much, right? It might help out a little bit sometimes, but it's not really changing how many extra protons or neutrons I have. Here, I'm actually taking a neutron and turning it into a proton, which is going to help that ratio and that stability quite a bit. And so that's what happens in beta particle decay. Your electron leaves the neutron, and it becomes a proton. Is everybody okay with that? Okay. So that's beta particles. Beta particles are denoted with a B. Everybody make sure they're awake and looking at the board. There we go. Beta particles are denoted with a B. They give you a -1 down here at the bottom where your protons should go. So it tells you you're subtracting. Wait, is that right? No. You're going to add a proton, and you'll see how this works with the math. A negative charge leaves, which should give you 1 extra charge in your new atom. So here's your formula. I have carbon. Carbon's going to radioactively decay. This is carbon-14. It's going to radioactively decay. I shoot out a beta particle, which has a negative charge, and it turns one of my neutrons into a proton. So 6 minus -1. If you minus a negative, what's going to happen? You're going to be adding. So I need to actually have nitrogen with 7 protons here in it. So you see, 7 plus -1 is equal to 6, right? Does that make sense for everybody? So if I'm switching this around, I would do 6 minus -1 gives me 7, and what I end up with is 7 protons, which is a nitrogen. Up top, B has a 0. Your number of neutrons plus protons doesn't change. That number is the same. I just had a neutron switch to a proton, and so technically the count is going to stay exactly the same. So you'll see a couple problems like this. Note, it's not the full weight that's leaving. Beta particles, unlike a alpha particle, which is a helium atom, they only weigh the mass of an electron. They're very, very small, very, very light. They're not anywhere close to the whole atom. What? My board died right? Nope, came back. Came back to life. So the next one is a positron. This is the other type of beta particle. So instead of shooting out an electron out of the nucleus, it's the opposite of an electron. It's a positron. It's going to shoot out a positive particle. So this is going to be denoted with another B, just like the beta. It's going to be a +1 instead. And essentially what happens is you have a proton now shoot out its positive charge. So instead of a neutron shooting out its negative and leaving that behind, you're going to have the proton shoot out its positive charge. It's just like an electron size. It's not the whole molecule. But if a proton gets rid of its positive charge, what is it now?
Electron.
It's getting rid of a positron, but it doesn't have a negative left over. What's left in it? Nothing, which would make it a neutron. Which I know I just told you that neutrons are nothing, but we're doing crazy stuff here with radioactivity. So in the positron thing, your positron gets shot out, It's like a positive electron, really tiny, really small, just a charge. What's left over is going to be your neutron. So same kind of math here. I have arsenic, which has 33 protons. I'm going to shoot out a positron, so my number of protons is actually going to go down. My number of protons plus neutrons on top, my mass number, stays the same. That 0 doesn't change it. So 33 is equal to 32 plus 1. 74 is equal to 74 plus 0. That's how you're doing these. You're just setting up the math equation, and you use the bottom number to tell you what you have. And I have it written down over here. So when you get to it, if you have a 2, it's going to be a helium atom or an alpha particle if you're talking about the radioactive particle. If it's a negative 1, it's going to be a beta particle. If it's a positive 1, it's going to be a positron. And then we'll get to gamma in just a second. So the last type, gamma radiation. What did gamma radiation give us? The Hulk, yes. Remember, it's not going to turn you into the Hulk. It's just going to give you like a painful death, which is not going to be fun. Gamma radiations are very, very high energy. It's electromagnetic radiation. So does light have any mass? No. So it's not a proton. It's not a neutron. It's not an electron. It doesn't have any charge. It's literally just pure energy released after an alpha or beta emission in some radioactive thing. So there's no mass. There's no change in your numbers. It's just energy that's shot out. So if you have an equation like that, they're not even going to do an equation because it doesn't even change anything. But no effect of the mass or atomic number when you have gamma radiation. It's just like a byproduct of really radioactive stuff. So they point out here, beta particles have 2 protons, 2 neutrons, and no electrons. So what's their charge? Positive. They have 2 protons and no negative charge. They're going to be positive. So they're going to actually go up away from the negative charge. Or wait, is that right? No, they got that wrong. Yeah, it would actually be flipped. Oh, wait, I'm sorry. I said beta, but I meant alpha. My bad. The alpha particle is positive, so yes, they're right. It's going to go down. It's going to be attracted to the negative plate and pushed away from the positive plate. Beta particles are going to be negative. They have a negative charge in them, just like an electron. They're going to be pushed away from the negative side and go towards the positive side. And then gamma particles down at the bottom have no charge, no protons, no electrons, nothing like that. They're just going to shoot straight through. They're not going to be affected by charge at all. What stops this radiation? Alpha particles are really large. It's basically like a helium atom. Can air pass through paper? No. And so a piece of paper will literally stop alpha radiation. It's not that bad. It's not too bad for you. It's not going to hurt you that much. Beta radiation is a little bit smaller. It's like an electron. Could an electron probably pass through a piece of paper? Yeah. And so it can pass through a piece of paper, but not 0.5 centimeters of lead. A little thin sheet of lead will stop your beta radiation. Gamma radiation has no mass. It has very high energy. It's going to blast through the paper, through the thin sheet of lead, like on your doctor's protective vest. But up to 10 centimeters of lead could stop some gamma radiation. So gamma radiation is very, very powerful. It's going to penetrate through a lot of objects, and it's going to be hard to kind of protect yourself from that. On the flip side, we don't really care about lead. What do we care about? Our own bodies. This is what your radiation is going to do to your body. Alpha particles will cause some light damage just on the skin, not on the tissue below the skin. If paper can stop it, your skin's going to stop it. It's not going to go too deep. Maybe not too bad of a problem. Very dense, short track of damage. Beta radiation is going to go a little bit further. It's going to go through your skin into some of the tissues down below, but it's going to stop shy of your organs. It's not going to damage your heart or your brain or your lungs or anything like that. Still could be a bad day for you, but it's going to be a lot less likely to kill you, at least immediately. And then finally, your gamma radiation, it's just going to go through everything and maybe even out the other side. And it's going to leave some pretty good damage all along the way. So it can damage your organs, your tissue underneath your skin, and your skin itself. Pretty bad stuff, the gamma radiation is. So try to stay away from radiation in all its forms. That's it for the PowerPoint. So go ahead and start the assignment. I will leave up this slide, which kind of shows you one of the math problems. But remember, you're just doing some math here, and you're trying to figure out what kind of change you had happen. I'll leave the beta particle one up. That'll help you out a little bit. And for those of y'all at home, because I got more people at home today than I did yesterday, sorry about that. Here is your charges for your alpha, beta, positron, and gamma particles. So it kind of shows you what they look like. Alpha is a helium atom with 2 protons and 2 neutrons. A beta particle is essentially just an electron, a negative charge leaving, doesn't change your protons or neutrons. A positron is essentially a positive electron, hence the word positron. And then gamma particles have no mass. They have no change to any of your numbers there. So if you have any questions, please send me an email, and I will get back to you, especially if you're, well, not especially. For anybody at home that has questions, send me an email, and I will I'll get back to you. So I hope you all have a nice day and do well in the assignment, and I will see you tomorrow.